Somewhere above you right now, past the ceiling, past the clouds, past the thin blue ribbon of the atmosphere that holds all of life together, there is a star moving at 3 million miles per hour. No destination, no orbit, no galaxy to call home. Just drifting. And the strangest part? It has been drifting alone for longer than our entire solar system has existed. Welcome, pull the blanket a little closer. Let your shoulders drop. Tonight we're going somewhere most telescopes can barely reach, into the deep, dark spaces between galaxies where stars wander without compass, without company, and without end. Stories the universe has been writing for billions of years in a language made entirely of gravity and light and silence. Before we drift any further, if you find yourself settling in, if this feels like the kind of place you'd like to return to on a quiet night, you can gently tap the like button. It takes just a moment, and it means more than you know. And if you'd like the next quiet journey to find you when it's ready, consider subscribing and ringing the little bell, not for noise, just so the universe knows where to send the next story. Now, let's begin. Cast your mind back to a sky without light pollution. A real sky, the kind that used to hang over every human who ever lived before, electricity before cities, before we learned to flood the dark with our own brightness. For most of human history, the night sky was the greatest mystery anyone had ever looked at. Ancient shepherds watched it, Babylonian priests mapped it, Polynesian navigators read it like a language, steering wooden canoes across thousands of miles of open ocean using nothing but stars and instinct. For all of them, the sky felt fixed, eternal, a ceiling of certainty. Almost everything in it seemed to stay still. Almost. There were exceptions. A handful of lights, 5, 6, 7, depending on how carefully you looked, that moved. Slowly, night by night, week by week, they traced paths across the background of the fixed stars. Though ancient Greeks had a name for them, asteres planetae, wandering stars. We now know those wandering stars were planets Mercury, Venus, Mars, Jupiter, Saturn, objects in our own solar system, following predictable paths around the sun. The Greeks were wrong about what they were, but in the deepest sense, they were right about the idea. Because it turns out there really are wandering stars out there, not planets mistaken for stars, actual suns. Real stars with histories stretching back billions of years, torn loose from their galaxies, flung into the abyss, traveling at speeds that should seem impossible through a darkness that should seem incomprehensible. And we only discovered them in 2005. Think about that for a moment. For all the millennia that humans have stared at the sky, for all the telescopes and satellites and radio observatories, we've built this entire category of object stars moving fast enough to escape galaxies entirely, was unknown to us until less than 20 years ago. The universe still has secrets, enormous ones. So, what exactly is a wandering star? Let's settle into the idea gently. When astronomers use the term today, they're usually referring to what they call hypervelocity stars. Stars that have been accelerated to such extreme speeds that they exceed the escape velocity of the Milky Way itself. Our galaxy has a gravitational pull just like Earth does, just like the sun does. If you throw something fast enough, it can break free. For Earth, that speed is about 25,000 miles per hour. For the entire Milky Way galaxy, a structure containing somewhere between 100 and 400 billion stars, spanning 100,000 light-years from edge to edge, the escape velocity from our position in the galaxy is roughly 550 kilometers per second. That's about 1.2 million miles per hour. Hypervelocity stars travel faster than that. Some of them travel at 2, 3, even 4 times that speed. They are in the most literal, physical sense stars that the galaxy cannot hold. And right now, several of them are already gone, already sailing out beyond the outermost rim of the Milky Way, into the vast, cold, near-empty ocean of intergalactic space, moving away from us at speeds our fastest spacecraft couldn't approach in 1,000 years. Here's a question worth sitting with tonight. What does it mean for a star to be truly alone? Not alone the way we sometimes feel alone, surrounded by a world breathing air with the warmth of a sun overhead. Alone the way a hypervelocity star is alone. No neighboring stars within light years, no planets circling, no dust clouds, no nebulae, no galactic structure in any direction. Just the star itself burning and the dark stretching away in every direction for hundreds of millions of light years, and the soft, faint, barely there glow of distant galaxy clusters far, far behind it, growing fainter by the millennium. Now, before we go any further, let's dissolve one of the most common misconceptions people carry about stars about the sky itself. We tend to think of stars as stationary, fixed. The word fixed stars has been used for centuries to describe the background of the night sky, as opposed to the planets. But that's an illusion born entirely of distance and time scale. Every single star you see tonight is moving. Our sun is moving right now as you breathe, as you read, as you drift towards sleep, hurtling around the center of the Milky Way at about 514,000 miles per hour. It has been doing this for the entire 4.6 billion years of its existence. In that time, it has completed roughly 20 full orbits of the galaxy. Astronomers call this the galactic year, or cosmic year 1. Full orbit takes about 225 to 250 million years. The last time the sun was in its current position in the galaxy, dinosaurs had not yet evolved. Before that, the first complex animals were only just beginning to appear on Earth. Everything moves, always. The stillness of the night sky is just the universe moving too slowly for us to watch in a single lifetime. But most stars move in more or less orderly ways, orbiting the galactic center, pulled and guided by the combined gravity of hundreds of billions of other stars, gas clouds, dark matter halos. They have paths, even if those paths take hundreds of millions of years to complete. Wandering stars have lost those paths. They've been severed from the gravitational web that holds everything else together. And that severing, that moment of cosmic violence or cosmic accident, is the beginning of their story. A story that starts as most of the most dramatic stories in astrophysics do near a black hole. Let's pause here just for a breath and appreciate the sheer scale of what we're considering. The Milky Way galaxy is not a small thing. If you tried to drive across it at highway speed, say 60 miles per hour, it would take you about 1.1 trillion years. The universe itself is only about 13.8 billion years old. You would need about 80 universes worth of time just to drive from one side of our galaxy to the other. And yet, some stars have escaped it. They've been moving long enough, fast enough that even the Milky Way's enormous gravitational reach, extending outward for hundreds of thousands of light years in every direction, cannot pull them back. When something is that fast, when it moves through something that vast and still breaks free, the word wandering starts to feel almost too gentle, too poetic. These are not gentle wanderers. They are refugees. They are the survivors of some of the most violent gravitational events in the known universe. And they carry those events in their speed, encoded in their motion, like a scar, or a memory, or a message in a bottle thrown into an ocean with no shores. There's something almost philosophical about it, isn't there? The idea that the same force gravity that holds galaxies together, that forms stars and planets and moons, that keeps your feet on the floor and your atmosphere from drifting away into space, that same force under the right circumstances, can also be the thing that flings a star into permanent exile. Gravity both binds and liberates. Depending on the geometry, depending on the timing, depending on the masses involved, an interaction that looks like a close encounter can become a slingshot. A near miss can become a launch. And a star that was once part of the structured, turning, gravitationally bound community of a galaxy can find itself suddenly moving in a direction and at a speed from which there is no return. Astronomers have compared it somewhat poetically to a gravitational three-body problem, a situation where the mathematics of motion becomes chaotic. When three massive objects interact, the equations that govern their paths can produce wildly unpredictable outcomes. One body might be ejected entirely, thrown out of the system with enormous velocity, while the other two settle into a tighter orbit. The one that leaves carries the energy. The ones that stay release it. Energy is never created in these interactions. It's transferred. And the star that gets thrown out carries the bill. Now, I want you to hold one more image before we move into the science of how all of this actually happens. Imagine standing on a beach at night. The ocean in front of you is enormous, dark, and full and endless in every direction your eye can reach. Behind you, a city. Warm lights. The hum of life. Everything connected, everything part of the same fabric. And then imagine at the edge of the water, you watch a single wave, not a ship, not a creature, but a wave of extraordinary energy roll outward, past the continental shelf, past the last shallow water, into the deep ocean where the bottom drops away and the pressure becomes something no living thing can survive. The wave doesn't stop. It can't stop. It simply moves, carrying its energy outward into a dark that has no horizon. That's a hypervelocity star. That's what it means to be cast out of a galaxy. And the universe is full of them, more than we've found, more than we've looked for, more than our current instruments can count. Patient, brilliant, ancient, and utterly alone. The question is, how does it happen? What in the universe is powerful enough, strange enough, precise enough to take a star and throw it out of a galaxy? The answer, as it so often is, in astrophysics involves a black hole. And not just any black hole, the one at the center of ours. That story begins just ahead in the dark heart of the Milky Way, where gravity bends not just light, but the fates of stars themselves. 4 million times the mass of our sun, sitting in silence at the center of the Milky Way, waiting, not with patience, not with intention, just waiting the way gravity always waits for something to come close enough. At the heart of nearly every large galaxy in the observable universe, there is a supermassive black hole, not a small one, not the kind formed when a single star collapses at the end of its life. Those are enormous by human standards, but modest by the scale of what we're talking about now. Supermassive black holes contain millions, sometimes billions of times, the mass of our sun compressed into a region of space so small, so dense, that not even light can escape once it crosses the boundary. That boundary has a name, the event horizon. And beyond it, physics as we know it stops making useful predictions. The black hole at the center of our galaxy is called Sagittarius. A star, pronounced Sagittarius, A star. It sits about 26,000 light years from Earth, in a region so crowded, so gravitationally turbulent, so filled with gas clouds and young stars and ancient stellar remnants that for most of human history, we couldn't even see it clearly. The dust between us and the galactic center absorbs visible light almost completely. It was only through infrared and radio observations, wavelengths of light that pass through dust, the way a radio signal passes through a wall, that astronomers began to piece together what was really happening there. And what was happening there was remarkable. Stars were orbiting something invisible, something impossibly massive, looping around an unseen center in tight, fast ellipses, some completing full orbits in just a few years. One star, designated S, 2 swings around Sagittarius. A star on an orbit that brings it within about 120 astronomical units of the black hole, at its closest approach roughly 3 times the distance from the Sun to Pluto. At that point, it's moving at about 7,650 kilometers per second. That's approximately 2.5% of the speed of light. With the naked eye, if you could somehow watch it, it would appear to travel across a space the size of the full moon in about 7 minutes. These stars near the galactic center are moving in a gravitational environment that is almost beyond imagination. And that environment, it turns out, is exactly where wandering stars are born. Here is the mechanism. Settle in, because this is one of the most elegant and most violent processes in modern astrophysics. Imagine a binary star system. 2 stars gravitationally bound to each other, orbiting their shared center of mass, the way a pair of dancers might circle each other. Binary stars are extraordinarily common. More than half of all sun-like stars in the Milky Way are thought to exist in binary or multiple star systems. Our sun is unusual in being a solitary star. Most stars have company. Now imagine this binary pair drifting over millions of years, gradually closer to the galactic center. Not because anything is specifically pulling them toward the black hole, simply because the complex gravitational dynamics of the galaxy's inner regions can slowly nudge stellar orbits inward over enormous time scales. They drift, they circle, they edge a little closer with each orbital period, the way a fallen leaf spirals slowly toward the drain of a bathtub. And then one day on a time scale that has no equivalent in human experience, they come close enough to Sagittarius, a star for something extraordinary to happen, the black hole's tidal forces. The difference in gravitational pull between the near side and far side of the binary pair becomes strong enough to rip the two stars apart from each other. This is called a tidal disruption interaction, and it happens with a kind of terrible precision. One of the two stars is captured. It falls into a tighter orbit around the black hole, or in some cases falls in entirely. The other star is flung outward using the orbital energy that the captured star has surrendered. It's like a gravitational slingshot. The captured star pays the price. The ejected star receives the reward. Except the reward in this case is ejection at a speed of hundreds of kilometers per second, sometimes more than 1,000. This process was first theorized by the astrophysicist Jack Hills in 1988, and it is now known as the Hills mechanism. For nearly 2 decades, it remained theoretical, an elegant piece of mathematics that predicted something no one had yet observed. Then in 2005, a young astronomer named Warren Brown, working with a team at the Harvard-Smithsonian Center for Astrophysics, found the first one, a star, moving at 709 kilometers per second, already well outside the Milky Way's main disk. Heading outward and showing no signs of slowing down, they named it SDSSJ 090745.0 plus 024507. Not the most poetic name in the history of astronomy, but what it represented was astonishing, the first direct observational confirmation that the Hills mechanism was real, that black holes at galactic centers really do hurl stars into intergalactic exile, that the universe, for all its slow and measured grandeur, is also capable of acts of extraordinary permanent violence. Now, here is where it gets even more interesting, and where one of the most common misconceptions about this process deserves to be gently corrected. Many people, when they first learn about hypervelocity stars, assume that the star must somehow have been swallowed by the black hole and then spat back out, that the black hole acts like some kind of cosmic cannon drawing things in and then ejecting them. That's an understandable mental model. It's intuitive, but it's not quite right. The black hole doesn't directly eject anything. It doesn't spit. It doesn't launch. What it does is far more subtle and in some ways more astonishing. It simply exists with its enormous gravity in close proximity to a binary system that already has orbital energy. When the tidal forces disrupt that binary, the energy that was stored in the orbital relationship between the two stars doesn't disappear. Energy never disappears. It redistributes. One star absorbs extra energy and is launched outward. The other loses energy and falls inward. The black hole is less a cannon and more a gravitational fulcrum, a lever point around which an enormous transfer of energy occurs in a fraction of a second. This distinction matters because it tells us something beautiful about physics. Even the most extreme outcomes in the universe are governed by the same conservation laws that apply in a high school physics classroom. Energy is conserved. Momentum is conserved. The universe keeps its books impeccably. The star that gets ejected didn't receive new energy from nowhere. It received energy that already existed, energy borrowed from the gravitational potential of its lost companion, transferred in the most dramatic way possible. But the galactic center is not the only place where stars can be born into exile. Astronomers have identified several other mechanisms that can strip a star from its galactic community, and each one tells a slightly different story about the violence that underlies the apparent serenity of the cosmos. Consider what happens when two galaxies collide. This is not a rare event on cosmological timescales. Galaxies are social objects. They exist in groups and clusters, bound to each other by gravity across millions of light years. And over billions of years, they drift toward each other, interact, and sometimes merge. The Milky Way itself is on a collision course with our nearest large galactic neighbor, the Andromeda Galaxy, a meeting that will begin in roughly 4.5 billion years and play out over hundreds of millions of years after that. When astronomers model these collisions, the images look almost gentle. Two vast pinwheels of light, slowly interpenetrating stars and gas clouds swirling into new configurations. Two black holes spiraling toward each other at the respective centers. But gentle-looking doesn't mean gentle. When galaxies interact, the gravitational perturbations can reach deep into stellar populations and disrupt orbits that have been stable for billions of years. Stars can be scattered. Clusters can be torn apart. And in the process, some stars acquire enough velocity to escape not just from the galaxy they started in, but from the merged system entirely. Flung outward by the gravitational chaos of two colliding stellar cities, they become intergalactic wanderers carrying in their spectra the chemical signature of a galaxy that may no longer exist by the time anyone is around to read it. There's something quietly moving about that isn't there. A star that formed in a galaxy now, gone absorbed, merged, transformed, still traveling, still burning, still holding within its light the record of its origin. There is a third mechanism less dramatic in its physics, but no less final in its outcome, and it involves something called a stellar cluster. Deep within galaxies, particularly in the dense, bulging centers, stars form in enormous clusters. Gravitationally bound groupings of tens of thousands, sometimes millions of stars, all born from the same collapsing cloud of gas and dust, within a relatively short span of cosmic time. These clusters are some of the most beautiful objects in astronomy. Globular clusters, the ancient spherical ones, can contain up to 1 million stars packed into a region just 100 light years across. Under certain conditions of sky darkness, the brightest of them, like Omega Centauri or 47 Tucanae, are visible to the naked eye, appearing as fuzzy stars. Inside these clusters, stars are far closer together than they are in the open galactic disk. And closer together means more frequent gravitational interactions. Stars pass near each other. Their gravity tugs. Their orbits shift. In a process called dynamical ejection, a close three-body encounter, two cluster stars, and a visiting third can transfer enough energy to the third star to kick it out of the cluster entirely. Most of the time, the ejected star simply escapes the cluster and joins the general stellar population of the galaxy. But sometimes, if the cluster itself is in a region of the galaxy where escape velocity is already relatively low, the ejected star can achieve enough speed to leave the galaxy as well. It's slower than the Hill's mechanism. The speeds are lower, but the outcome is the same: a star without a home moving outward through darkness with no gravitational anchor remaining. Let's take a moment to appreciate something that isn't often discussed when people talk about wandering stars: the question of what they might carry with them. When astronomers study a hypervelocity star, one of the first things they want to know is its chemical composition, its metallicity, in the language of astrophysics, which doesn't mean metal in the everyday sense, but rather the proportion of elements heavier than helium that the star contains. Stars formed early in the universe's history have very little of these heavier elements because those elements, carbon, oxygen, iron, silicon, were mostly made inside stars and distributed by supernovae over billions of years. The universe had to cook them up. Early stars didn't have access to them. Later stars formed from gas clouds already enriched by previous generations of stellar explosions, have much higher metallicity. The metallicity of a hypervelocity star tells you something about where and when it formed, and in some cases, it tells you a story that is almost heartbreaking in its scope. There are hypervelocity stars that formed that were born near the galactic center in one of the richest, most chemically complex environments in the galaxy. They had whatever might be called a privileged origin surrounded by ancient stellar populations and the churning energetic environment of a supermassive black hole. And then, in a single gravitational interaction, lasting less time than it takes a hummingbird to beat its wings, they were separated from all of that, flung outward, set on a course from which there is no return. They carry their chemistry with them, like a passport proof of where they came from, evidence of a home they will never see again. Here is a question worth holding quietly for a moment. Do any of these wandering stars have planets? It is a question that current technology cannot fully answer. The methods we use to detect planets around distant stars, transit photometry, radial velocity. Measurements require long baseline observations and are most effective for nearby stars. Hypervelocity stars are almost by definition far away and moving fast. They are hard to study in detail, but the physics doesn't forbid it. A star ejected by the Hills mechanism, for instance, was once part of a binary system. If it had formed planets around it before the disruption event, some of those planets might have survived. Depending on how the disruption occurred, how close the binary came to the black hole, how the energy was distributed, some planets in stable inner orbits might have stayed with the ejected star. If so, they are now moving through intergalactic space on a journey with no end, orbiting a star that orbits nothing, carried along into the permanent dark. Whether they retain the conditions for anything resembling life is a question that spirals into territory where science shades gently into philosophy. But the universe has surprised us before. What all three mechanisms share the Hills mechanism near a supermassive black hole, the gravitational chaos of galactic collisions, the dynamical ejections from dense stellar clusters, is that they are all expressions of a single deep truth about gravity. Gravity is not a gentle force. We experience it as familiar, constant, reassuring the force that holds our tea in our cup and keeps the moon in its quiet orbit. But at scale over time, in the presence of masses that dwarf anything in our daily experience, gravity becomes something else entirely. It becomes the architect of exile. It becomes the force that separates what was bound, that accelerates what was slow, that casts into permanent darkness what was once surrounded by light. The universe builds communities of stars, galaxies, clusters, associations, and then with the same mathematics, slowly and inevitably dismantles some of them. Not all stars are allowed to stay. Some are chosen not by any intention, only by geometry and timing to leave. They are the solitary suns, and they are in their silence one of the most extraordinary things our universe has made. The question now is, how fast do they actually travel? Because the numbers, when you let them settle in properly, will make you feel the size of space in a way that very few things can. Let's start with a number, 709. That's kilometers per second. Now let's put that in terms that actually land somewhere in the human body. The fastest bullet ever fired by a military rifle moves at about 1.7 kilometers per second. The fastest spacecraft humanity has ever launched, the Parker Solar Probe, reached about 163 kilometers per second at its closest approach to the sun, and it took the entire gravitational pull of our star to get it there, 709 kilometers per second. That was the speed of the very first hypervelocity star ever confirmed, and it wasn't even the fastest one. Speed is one of those things the human mind handles poorly at large scales. We are evolved to perceive motion that matters to survival, the sprint of a predator, the arc of a thrown stone, the drift of a river current. We can feel fast at 60 miles per hour in a car. We can feel the exhilaration of a plane lifting off at 180. But somewhere around a few thousand miles per hour, our intuition stops updating. The numbers become abstractions. We say that's fast the way we say that's far. When someone tells us a star is 400 light years away, the words arrive, but the meaning doesn't quite get through. So let's do this carefully. Let's actually feel the speed of a hypervelocity star, one comparison at a time until the number has real weight. Sound travels through air at roughly 343 meters per second, about 0.343 kilometers per second. The first confirmed hypervelocity star, moving at 709 kilometers per second, travels at more than 2,000 times the speed of sound. If it were moving through Earth's atmosphere, which it isn't, but imagine it would cross the continental United States from the Pacific coast to the Atlantic in about 6.4 seconds. Light travels at 299,792 kilometers per second. A hypervelocity star moving at 709 kilometers per second is traveling at about 0.24% the speed of light. That sounds small, but consider the fastest particle accelerator on Earth. The Large Hadron Collider at CERN accelerates protons to 99.9999991%, the speed of light. But those are subatomic particles with essentially no mass. A star, a thing with the mass of our sun or more, moving at nearly 0.25% of light speed. The energy contained in that motion is almost incomprehensible. Now consider that some hypervelocity stars move significantly faster than that first one. US 708-1, of the most intensively studied hypervelocity stars, discovered in 2005 and confirmed at high velocity in subsequent years, is estimated to be traveling at approximately 1,200 kilometers per second. That's about 0.4% the speed of light, about 750 miles per second, about 2.7 million miles per hour. It is at the time of current research one of the fastest stars ever measured in the Milky Way. And unlike the first confirmed hypervelocity star, US 708, almost certainly did not originate from the Higgs mechanism at the galactic center. It has a different story entirely, one we'll return to shortly. Here is a misconception worth addressing directly, because it comes up almost every time someone first encounters this topic. When people hear the fastest stars in the galaxy, they often assume these must be young stars, recently formed, perhaps still surrounded by the gas clouds that birthed them, energetic and bright and new. It seems intuitive that something moving that fast should be young, vigorous, recently kicked. But that's not necessarily true. And the reasons why tell us something important about how stars age and how the cosmos stores energy across time. Many hypervelocity stars are not young at all. Some are what astronomers call late-type stars that have already evolved off the main sequence, already burned through much of their hydrogen fuel, already swelling toward or past the subgiant or giant phase. Some are what are called blue horizontal branch stars, older stars that have already gone through a red giant phase and are now burning helium in their cores. US 708. The fast one is actually a hot subdwarf star, a category of compact helium-burning, stellar remnant thought to form through specific binary interaction pathways. The age of a hypervelocity star doesn't change its speed. Whatever kick it received, whether from the Higgs mechanism 1 billion years ago, whether from a supernova in a binary system, whether from some other dynamical process that energy is still there. The star has been carrying it ever since. Speed in the vacuum of space doesn't dissipate. There's nothing to slow it down. A star set in motion 1 billion years ago is still moving at the same speed. Today, give or take, the very slow, very gentle deceleration caused by the galaxy's residual gravitational pull acting against it at enormous distance. This means that some of the wandering stars now beyond the galaxy's edge are ancient. They left the Milky Way, or were set on course to leave when Earth itself was young, or when the first complex life was just beginning to emerge in the shallow Precambrian seas. And they have been traveling continuously in the same direction at the same speed ever since. Time does not slow them. Distance does not tire them. They simply go. Let's spend a moment with US 708, Because its story is genuinely unlike any other we have discussed so far, and it introduces a mechanism for stellar ejection that is completely different from the gravitational slingshot of the galactic center. US 708 is a hot sub-dwarf, a small hot compact star that burns helium rather than hydrogen. It's moving at roughly 1,200 kilometers per second, already well outside the plane of the Milky Way, on a trajectory that will carry it into intergalactic space. When researchers studied its motion in detail, specifically its proper motion across the sky, measured by comparing its position in images taken years apart, they found something unexpected. The trajectory traced backward does not point toward the galactic center. It doesn't trace back to Sagittarius A star. It comes from a different part of the galaxy entirely. This meant the Hill's mechanism couldn't explain it. Something else had thrown US 708 at that speed. The leading explanation involves a particular kind of stellar violence, a Type 1, a supernova in a binary system. Here is how it works. US 708. In its earlier life was the companion star in a tight binary system. Its partner was a white dwarf, a dense stellar remnant roughly the size of Earth, but with the mass of a star sitting close enough to US 708 to strip matter from its surface. White dwarfs have an upper mass limit known as the Chandrasekhar limit at approximately 4 times the mass of the Sun. When a white dwarf accretes enough mass to approach or exceed that limit, the result is catastrophic. The white dwarf undergoes runaway thermonuclear fusion. The entire star detonates in a matter of seconds. A Type 1, a supernova, one of the brightest and most energetically consistent explosions in the universe, so reliable in its luminosity that astronomers use them as standard candles to measure cosmic distances. When the white dwarf exploded, the binary systems ceased to exist. The gravitational bond holding US 708 in orbit was severed in an instant, and like a stone released from a sling at the moment of maximum velocity, US 708 flew outward carrying its orbital velocity plus the momentum it received from the asymmetric push of the explosion at over 1,000 kilometers per second. It was flung not by a black hole, but by the death of its companion. There is something almost unbearable about that image if you let yourself sit with it. US 708 was not a solitary star by nature. It had a partner. They were bound together, close exchanging matter, existing in a relationship that had lasted astronomers' estimate for a very long time. And then, in an explosion that lasted seconds, its partner was gone. And US 708 was free moving, faster than it had ever moved free in the most complete and irreversible sense, heading into darkness that will only deepen as the millennia pass. Freedom and exile in that moment were the same thing. Now we've established two distinct origins for hypervelocity stars: the galactic center mechanism and the supernova ejection. But the question of how many such stars exist in and around the Milky Way is one that remains genuinely open, and the answer as research continues keeps getting more interesting. When Warren Brown and his team published their 2005 discovery, the expectation was that hypervelocity stars would be rare exotic objects produced by rare events difficult to find, possibly numbering only in the dozens. Subsequent surveys began to challenge that assumption. By the time the Sloan Digital Sky Survey had cataloged millions of stellar spectra, Brown's team had identified dozens of candidate hypervelocity stars, unbound stars, with velocities suggesting they are headed out of the galaxy for good. Then came Gaia. The European Space Agency's Gaia mission, launched in 2013 and still operating as of this telling, is arguably the most ambitious astrometric survey ever attempted. Its goal to measure the position and motion of approximately 1 billion stars in the Milky Way, with extraordinary precision charting the three-dimensional structure of the galaxy in a way never before possible. Gaia measures the tiny angular shifts in stellar positions as Earth orbits the Sun, a technique called parallax, to determine distances. and it measures the Doppler shift of starlight to determine velocities along the line of sight. Gaia's data releases have been transformative for the study of hypervelocity stars. In the second major Gaia data release, astronomers sifting through the catalog found hundreds of stars with velocities that, when combined with distance estimates, suggested they might be unbound to the Milky Way. Not all of these will withstand closer scrutiny. Some velocities have uncertainties large enough to leave the question open. But even if a fraction of them are confirmed as true hypervelocity stars, the total population of stellar exiles is far larger than anyone imagined in 2005. The universe, it turns out, throws things out much more often than we thought. And here is where the science opens into something that genuinely invites wonder rather than just measurement. Consider the path of a hypervelocity star once it has left the Milky Way. It is moving through what astronomers call the local group, the gravitationally bound collection of galaxies that includes the Milky Way Andromeda, the Triangular Galaxy, and about 50 smaller satellite galaxies scattered across a region roughly 10 million light-years across. Even at speeds of over 1,000 kilometers per second, crossing the full extent of the local group would take billions of years. The star would pass through regions of extraordinarily low density, almost empty space, with perhaps 1 atom per cubic meter on average, compared to the 1 million or so atoms per cubic meter in the tenuous outer reaches of the Milky Way's halo. During that journey, if journey is even the right word for a trajectory with no destination, the star would see the universe from a perspective no astronomer on Earth has ever had. Looking back, it would see the Milky Way receding, first the bright disk, then the halo, then the faintest outer regions of the galaxy, fading into a smear of light. Then, after millions of years, just a galaxy among galaxies, one bright point in a field of many. At some point, moving far enough and fast enough, even the local group would begin to recede behind it. And then it would enter the vast emptiness between galaxy groups, the cosmic web's voids, where the nearest galaxy might be tens of millions of light years in any direction. Have you ever tried to imagine true emptiness? Not a quiet room, not a dark night, not even the surface of the moon. True emptiness space, so void of matter that there is almost nothing in any direction for light years upon light years upon light years. That is where these stars are going. That is the universe they are entering. Before we leave the subject of speed entirely, there is one more comparison worth making, one that grounds all of this in something closer to home. The Voyager 1 spacecraft launched by NASA in September 1977 is humanity's most distant artifact. As of recent measurements, it is traveling at about 17 kilometers per second relative to the Sun, a speed it achieved through gravity assists from Jupiter and Saturn, the outer solar system's giants, lending their orbital energy to give this small probe its escape velocity. At 17 kilometers per second, it has taken Voyager 1 more than 45 years to reach the edge of the heliosphere, the bubble of solar wind influence that defines the rough boundary of our solar system. A hypervelocity star moving at 709 kilometers per second would cover that same distance in about 15 months. US 708 at 1,200 kilometers per second would do it in about 9 months. And these stars have been moving for millions, sometimes billions of years. The distance they have covered, the sheer expanse of void they have already crossed, is a number that no human intuition can fully hold. It can only be received quietly, the way one receives the sound of wind through trees in the dark, not fully understood, but felt. These stars are out there right now, moving, burning, carrying their ancient chemistry and their enormous velocity into a darkness that has no edge, alone in a way that has no earthly equivalent. And they have been alone, many of them, for longer than our planet has existed. What remains then is to understand what that darkness actually is, what it feels like in physical terms, to exist in the space between galaxies. Because intergalactic space is not simply empty, it is something stranger than that. Something colder, something almost impossibly still. Picture the emptiest place you have ever been. Maybe a desert at 3 in the morning. Maybe a frozen lake in winter miles from any road. Maybe a field so dark that the Milky Way casts a shadow. Now, take everything out of that place. Every molecule of air, every grain of dust, every photon of scattered light. Keep going. Remove 10 million times more than that. You are still not close to the emptiness of intergalactic space. We have been talking about speed, about the extraordinary velocity of wandering stars, the gravitational violence that launches them, the mathematics of escape. But speed alone doesn't capture what it means to be a star between galaxies. To understand the fully, we have to understand the environment these stars are moving through. Because intergalactic space is not simply the absence of stars. It is a physical environment with its own properties, its own temperature, its own faint and ancient light, and it is stranger, colder, and more profoundly empty than almost any analogy can reach. Let's begin with density. Inside a galaxy like the Milky Way, the interstellar medium, the gas and dust that fills the space between stars, has an average density of roughly 1 atom per cubic centimeter. That number itself is staggeringly low by any earthly standard. The air you are breathing right now contains approximately 27 quintillion molecules per cubic centimeter. That's 27, followed by 18 zeros. The interstellar medium, by comparison, is essentially a vacuum. And yet, by cosmic standards, it is relatively rich. It contains hydrogen gas in various phases, helium trace amounts of heavier elements, dust grains, magnetic fields, cosmic rays. It is the raw material of future stars, the recycled remnant of past ones. Even in its thinness, it is a medium of remarkable chemical and physical complexity. Intergalactic space has roughly 1 atom per cubic meter, not cubic centimeter. Cubic meter. A space roughly the volume of a washing machine containing a single atom on average, sometimes less. The intergalactic medium, the diffuse gas that permeates the voids between galaxies, is so thin that if you tried to pump it into a laboratory container and measure it with conventional instruments, your instruments would read 0. It registers only through the cumulative absorption of background light over millions of light years of path length showing up as faint spectral lines in the spectra of distant quasars. It exists technically, but barely. A wandering star moving through this medium encounters essentially no resistance, no material, no chemistry. It burns in a sea of almost nothing. Now consider temperature. And here is one of the most counterintuitive facts about intergalactic space, one that surprises almost everyone who first encounters it. The intergalactic medium is not cold in the way most people imagine. The common intuition is that deep space must be bitterly absolutely cold, close to absolute 0. The theoretical lower bound of temperature at minus 273.15 degrees Celsius. And in some very specific places, that intuition is almost correct. The cosmic microwave background radiation, the afterglow of the Big Bang suffusing all of space, has a temperature of approximately 2.7 Kelvin, just 2.7 degrees above absolute 0. Objects in deep space that are not generating their own heat and are well shielded from any radiation source will eventually cool toward that temperature. But the intergalactic medium itself, the thin gas between galaxies, is actually extraordinarily hot in terms of particle temperature. Measurements from X-ray telescopes reveal that much of the intergalactic medium exists in a state called the warm-hot intergalactic medium, or WIM, with temperatures ranging from about 100,000 Kelvin to 10 million Kelvin. That is hotter than the surface of most stars. In some regions of dense galaxy clusters, the intracluster medium, a richer cousin of the intergalactic medium, concentrated within galaxy clusters, reaches temperatures of tens of millions of Kelvin, making it one of the hottest diffuse substances in the observable universe. How can something so empty be so hot? The answer is one of the more elegant pieces of cosmological physics. The intergalactic gas was heated and continues to be heated by the gravitational energy released during the formation of large-scale cosmic structure. When matter fell into the gravitational wells of galaxy clusters and cosmic filaments billions of years ago, that infall converted gravitational potential energy into kinetic energy, which was then thermalized, converted into heat. The same process that makes a meteor glow when it falls into Earth's atmosphere operated on cosmic scales, heating diffuse gas to millions of degrees. Additionally, energy from active galactic nuclei, the supermassive black holes at the centers of galaxies, actively feeding and releasing enormous jets of radiation and plasma, continues to pump energy into the surrounding intergalactic medium, keeping it hot. So, a wandering star is moving through gas that is technically millions of degrees in temperature, and yet it would feel nothing. The gas is so vanishingly thin, 1 atom per cubic meter, that the total amount of energy it could transfer to the star's surface is essentially zero. Temperature in a gas is a measure of the average speed of individual particles. A million-degree gas with effectively no particles is still, from a macroscopic standpoint, nearly nothing. The star passes through it the way a ship passes through ocean mist, technically encountering it practically unaffected. There is something else in intergalactic space that deserves attention light, or more precisely, the profound quality of darkness that characterizes these regions, punctuated only by the most ancient, most dilute, and most uncanny illumination in the universe. A star within the Milky Way receives light from a sky full of neighbors. Our sun, for instance, sits in a region of the galaxy where thousands of other stars are close enough to contribute measurable amounts of light, though not enough to illuminate the night sky significantly, because stellar luminosity falls off with the square of distance. Still, there is a galactic context. A star in the Milky Way knows, in a purely physical sense, that it is surrounded by a community of other light sources. A hypervelocity star that has left the galaxy is in a different situation entirely. At a distance of, say, 1 million light-years from the Milky Way, well within the journey, such a star might complete over cosmic time. The Milky Way would appear as a faint, elongated smear of light in the sky, roughly the apparent brightness of the large Magellanic Cloud as seen from Earth. A galaxy, the entire Milky Way, all 400 billion stars, reduced to something you might not notice unless you knew to look for it. Andromeda might be slightly brighter or similar depending on position. The nearest large galaxy clusters the Virgo cluster. The Fornax cluster would be barely visible, specks there, hundreds of galaxies merging into single dim points at that distance. The sky from intergalactic space is dark in a way that the sky from Earth never is. It is not the darkness of a cloudy night, or even the darkness of the deep ocean. It is the darkness of genuine cosmic isolation, a sky filled with galaxy clusters that are so far away they provide essentially no local illumination, and with the faint, smooth, omnidirectional glow of the cosmic microwave background, which is below the threshold of visible light entirely. It is visible only with instruments sensitive to microwave radiation, not with any eye. A wandering star, if it had eyes, if any orbiting world with any kind of life were carried along with it, would look out into a sky almost entirely devoid of the kind of scattered light we take for granted. The universe would be visible as a vast three-dimensional web of faint light. The cosmic large-scale structure, galaxy filaments, and sheets and clusters spread across hundreds of millions of light-years in every direction, separated by enormous dark voids. It would be a view of the universe that no civilization within a galaxy has ever had. A view from the outside, a view from the margins. Can you picture that for a moment? Lying on the surface of a world orbiting a wandering star in the void between galaxies, looking up not at a galaxy's disk, but at the entire cosmic web, all of the universe's large-scale structure spread around you in every direction, like a city scene not from a street, but from an airplane at 40,000 feet at night with all the lights on. Let us now address a misconception that is particularly persistent and particularly interesting about the nature of intergalactic space. Many people assume that the voids between galaxies are completely featureless, that there is simply nothing there except empty space. The word void encourages this, as does the popular image of galaxies as isolated islands in a sea of nothing. But this picture is significantly incomplete, and the incompleteness has become one of the most active research frontiers in modern cosmology. The large-scale structure of the universe is not random. It is not even approximately uniform on large scales. Dark matter, especially the invisible gravitational scaffolding that makes up roughly 27% of the universe's total energy content, is arranged in an intricate cosmic web, dense knots at the intersections of filaments. Long tendrils stretching between those knots, flat sheets or walls where filaments meet, and enormous voids regions tens to hundreds of millions of light years across, where matter density is significantly below the cosmic average. These voids are not empty. They contain diffuse gas. They contain the faintest galaxies, dwarf galaxies that barely qualified as galaxies at all, spread thinly across their interiors. Some contain isolated, lonely galaxies that formed in a region of space that was never dense enough to assemble a cluster or even a significant group. And threading through everything through voids and filaments and cluster outskirts alike is dark matter, invisible, interacting, only gravitationally detectable, only through its effects on the motion of visible matter. A wandering star crossing an intergalactic void is moving through dark matter. The density is extraordinarily low, far too low to have any measurable effect on the star's motion, but it is there. The star is never technically moving through true nothingness. Even in the deepest voids, the universe has left traces of itself. Structure persists even at vanishing densities. The web was woven everywhere, even in the places that look from a distance most like nothing at all. There is one more physical characteristic of intergalactic space that rewards attention, because it connects the wandering star's environment to one of the deepest questions in modern astrophysics, the expansion of the universe itself. Space is not static. It expands. This is the central observational discovery of 20th century cosmology, Edwin Hubble's 1929, finding that distant galaxies are receding from us at velocities proportional to their distances, a relationship now known as Hubble's law. The universe is not a fixed container. It is a fabric that stretches, carrying galaxies with it as it expands, increasing the distance between all unbound objects over time. A hypervelocity star moving through intergalactic space is subject to this expansion. As it travels the very space it is moving through stretches, the galaxy it departed is receding, not just because the star is moving away from it, but because the universe itself is expanding beneath them both. At very large distances beyond roughly 5 billion light years, the expansion of space begins to exceed the ability of any object, no matter how fast, to close the gap. This is the basis of the cosmic horizon, a distance beyond which nothing can ever reach us, not because it is too far away today, but because space is expanding faster than light can cross the growing gulf. A wandering star moving at even 1,000 kilometers per second cannot outrun cosmic expansion if it travels long enough and far enough. Eventually, over time scales so vast they make the current age of the universe look like an afternoon, the expansion of space will dominate over its velocity relative to any nearby galaxy. It will become not just isolated from the Milky Way, but cosmologically isolated beyond any possibility of interaction with any observable region of the universe, moving through a space that is in every practical sense infinite and alone. This is the final destination of a wandering star, not a place, not a moment, simply an increasing distance from everything for as long as the star burns, and then darkness, and then the slow, eventual decay of what remains in a universe so expanded that even the echo of light is too dilute to find: silence. That is the word that keeps returning when the physics is fully assembled. Not silence as a poetic metaphor, but something closer to physical reality, an environment so empty of matter that even the concept of sound has no meaning. No medium for vibration, no air to carry a wave, no neighboring object close enough to reflect anything. Just the star burning in a darkness so complete and so vast that it renders our most extreme human experiences of solitude the loneliest room, the darkest night, the most distant place anyone has ever traveled, into something almost cozy by comparison. And yet, the star is not nothing. It is still a star, still fusing hydrogen into helium, or helium into carbon at its core, still generating light and heat and the slow, steady radiation that has continued uninterrupted since the star's birth. If it has planets, and some may, they are still there, still orbiting, still receiving what warmth the star has to offer, still completing their years in the same quiet way they always have. The wandering star does not know it has wandered. It simply burns. All of which brings us to a question that sits at the intersection of astrophysics and something older. What happens to the worlds that might be carried along with these stars? What becomes of a planet, a world like ours? Perhaps with oceans, perhaps with an atmosphere, perhaps with something more when its sun is ripped from a galaxy and sent into the permanent dark. That story belongs to the rogue planets, and it is even stranger than you might expect. There is a world out there right now with no sun, no star warming its face, no dawn, no noon, no dusk. Just the permanent dark of open space and a frozen surface that has not seen light in longer than our species has existed. And according to current estimates, there may be more of these worlds than there are stars in the Milky Way. We have been drifting with the wandering stars, those solitary suns cast out of galaxies burning alone through the spaces between worlds. But there is a parallel story unfolding alongside theirs, one that is quieter, darker, and in some ways even more haunting. It is the story of the rogue planets' worlds without suns drifting through the galaxy and sometimes beyond it in a darkness so complete that the very concept of a sky becomes meaningless. A rogue planet, also called a free-floating planet or an interstellar planet, is exactly what the name suggests. A planetary mass object that is not gravitationally bound to any star. It moves through space independently following its own path, around the galactic center, or in some cases escaping the galaxy entirely. It has no host, no warmth from above, no tidal tugging from a nearby stellar companion. It simply drifts in the dark through a universe that does not appear to notice it. The concept is not new. Planetary scientists and theorists had speculated about such objects for decades, ever since it became clear in the 1990s and early 2000s that planet formation is a messy, chaotic, energetic process, not the clean, ordered assembly that early solar system models implied. But confirmation of real rogue planets in significant numbers came slowly, and the science of finding them is still evolving. What that science has revealed so far is extraordinary enough to reframe how we think about planets, about stars, and about the relationship between the two. To understand rogue planets, we need to understand how planets are lost, the standard model of planetary formation. The core accretion model describes a process that begins with a protoplanetary disk, a flat rotating cloud of gas and dust surrounding a newly formed star. Over millions of years, dust grains collide and stick together, growing from millimeter-scale aggregates into centimeter rocks, meter-scale boulders, kilometer-scale planetesimals, and eventually planet-sized bodies. It is a process driven by gravity, by electrostatic forces at small scales, and by the sheer statistical inevitability of collision when enough material is orbiting in the same plane over long enough timescales. But the process is not tidy. Not every body that forms in a protoplanetary disk stays there. The gravitational interactions between forming planets, especially between a growing gas giant and the smaller bodies sharing its disk, can be dramatically destabilizing. A large planet migrating inward through its disk, for instance, can scatter smaller planets outward. Two planets in resonant orbits can exchange energy through repeated gravitational nudges until one of them crosses a critical threshold and is ejected entirely. In multi-star systems, the gravitational influence of a companion star can perturb planetary orbits over long time scales, slowly pumping up their eccentricities until one day, a planet that was in a stable orbit for millions of years finds itself on a hyperbolic trajectory, escaping the system entirely. This is how rogue planets are born, not through any single dramatic event necessarily, but through the slow accumulation of gravitational perturbations, or through the rapid violence of a close planetary encounter, or through the ejection that accompanies the kind of stellar disruption events we explored in earlier parts of this story. Planets are not guaranteed to stay. They are only as secure as the gravitational architecture of the system they inhabit. And that architecture is never perfectly stable. Over the billions of years a planetary system typically exists. How many rogue planets are there? This is a question where the numbers have shifted dramatically as observational techniques have improved, and where each new data set seems to push the estimate upward rather than downward. Early estimates based on microlensing surveys of the galactic bulge in the 2000s and 2010s suggested that Jupiter-mass rogue planets might be roughly as common as main sequence stars, meaning there could be hundreds of billions of them in the Milky Way alone. A 2011 study based on microlensing data from the MOA and OGLE surveys published in the journal Nature proposed that Jupiter-sized free-floating planets might outnumber main sequence stars by nearly 2 to 1. That paper made headlines worldwide, and it fundamentally changed how astronomers thought about the planetary census of the galaxy. Then came results suggesting that smaller rogue planets, Earth mass, and sub-Earth mass free floaters might be even more numerous. Some models of planet formation and ejection predict that low-mass planets are easier to eject than high-mass ones because they are more susceptible to gravitational scattering. If that is correct, the true population of rogue planets in the Milky Way could easily exceed 1 trillion. 1 trillion worlds with no suns. The James Webb Space Telescope, launched in December 2021, has begun to add direct observational weight to these estimates. In observations of the Orion Nebula star-forming region, one of the most actively studied stellar nurseries in the galaxy, located about 1,300 light-years from Earth, Webb detected a population of free-floating planetary mass objects between roughly 0.6 and 13 Jupiter masses. Some of these appeared to exist in pairs loosely bound to each other by gravity, a configuration astronomers have nicknamed Jupiter mass binary objects, or jumbos, a finding so unexpected that it generated immediate debate about whether these objects formed through ejection from stellar systems or through some kind of direct gravitational collapse in regions too small and too low mass to form stars. The debate is not yet resolved. But the implication is clear: the galaxy is populated with worlds that have no suns in numbers that dwarf the number of stellar systems. Planets, it seems, are not rare, and wandering planets free cold dark may be the most common category of world in the observable universe. Now here is the question that deserves the most careful and honest engagement, because it is the one that almost everyone asks, and the one where the science is genuinely more open than popular accounts sometimes suggest. Could a rogue planet support life? The immediate intuition is, of course, not. A planet with no star has no sunlight, no photosynthesis, no obvious energy source for a biosphere. The surface would be frozen, not merely cold, but frozen at temperatures approaching the cosmic microwave background, somewhere around negative 270 degrees Celsius, close to absolute zero. No liquid water, no atmospheric chemistry driven by stellar ultraviolet radiation, no seasons, no days, no light. That intuition is not wrong exactly, but it is incomplete. Consider what we now know about the conditions under which life persists on Earth. Life is not, it turns out, exclusively a surface phenomenon. Some of the most extreme and most ancient forms of life on Earth exist in conditions that would kill most surface organisms instantly. Hydrothermal vent communities on the deep ocean floor thrive in complete darkness at crushing pressures around superheated water, laced with sulfur compounds deriving energy not from sunlight, but from the chemical gradients between hot vent fluid and cold ocean water. These chemolithotrophic organisms, literally rock-eating life, are completely independent of solar energy. They have been there functioning for at least billions of years, utterly indifferent to what the sun is or is not doing. Now, consider this a rogue planet with a rocky or icy composition, and sufficient size would retain internal heat from multiple sources. Radioactive decay, the slow breakdown of isotopes like uranium, 238 thorium, 232, and potassium-40, present in rocky planetary interiors throughout the universe, generates heat continuously on timescales of billions of years. For a planet of sufficient mass, this radiogenic heating alone can maintain a liquid water ocean beneath a thick ice shell for extraordinarily long periods, even in the complete absence of a star. Additionally, tidal heating, the flexing of a planet's interior by the gravitational pull of a companion, which keeps Jupiter's moon Europa liquid, would not apply to a truly isolated rogue planet. But radiogenic heating alone may be sufficient. Some astrobiologists have proposed that rogue planets with thick hydrogen atmospheres, a possibility for some classes of free-floating worlds, could retain enough greenhouse warming to maintain liquid water at their surfaces, even without a star, if their atmospheres were dense enough to trap internal heat. The physics is plausible, though. The conditions required are stringent and the scenarios speculative. But speculative in science means not yet confirmed, not impossible. There is a distinction that is worth drawing carefully here, because it gets muddled in popular discussions fairly often. A rogue planet is not the same as a wandering star with planets. A wandering star, a hypervelocity star, cast out of the galaxy, might carry planets with it, as we touched on briefly in Part 2. Those planets would still have a sun, still receive light, and heat, still have the benefit of stellar energy, even in the vast darkness of intergalactic space. Their situation is extreme, far from any galaxy orbiting a star that is itself in permanent exile, but it is categorically different from a rogue planet which has no star at all. A rogue planet is more alone than a wandering star's world. It has lost not just its galactic community, but its star. It carries nothing with it except whatever internal heat remains, whatever thin atmosphere has not yet frozen out onto its surface, and whatever chemistry accumulated during the brief bright period of its formation, when a star was still overhead and things were comparatively warm. This distinction matters because it clarifies the two different kinds of cosmic solitude we are discussing. The wandering star is an exile with companions, however faint and far, the light however cold the void there is, still a fusion furnace at the center of its planetary family. The rogue planet is in a deeper category of alone. It is a world that has been in the most complete physical sense abandoned. Let's visit one of the most well-studied candidate rogue planets to ground all of this in something specific. CFB-D SIR 2149-0403 is a free-floating planetary mass object discovered in 2012 by astronomers using data from the Canada-France-Hawaii telescope and other observatories. Initial analysis suggested it might be a young object approximately 4 to 7 times the mass of Jupiter moving through space with no stellar host. Its estimated surface temperature and rogue planets, like all sufficiently massive bodies, have surface temperatures above absolute zero due to residual formation, heat, and ongoing gravitational contraction, was around 700 to 800 Kelvin, hot by surface standards, still fusing nothing, still dark in the sense of producing no nuclear energy, just slowly cooling. More recent analysis has introduced some uncertainty about whether CFB-DSIR 2149-0403 is truly a rogue planet, or a very low-mass brown dwarf, a category of failed star that straddles the boundary between planet and star. That boundary, for the record, is conventionally placed at about 13 Jupiter masses, the minimum required for deuterium fusion. Objects below that threshold are technically planets, regardless of whether they formed in a disk or by direct collapse. The debate around CFB DSIR 2149-0403 illustrates something important. At the boundary of categories star, brown dwarf, planet, the universe does not always cooperate with our desire for clean definitions. What is not in question is that free-floating planetary mass objects exist, that they move through the galaxy without stars, and that their surfaces cooling slowly over billions of years, still warmer than the surrounding space, glowing faintly in infrared wavelengths that no human eye can see, are among the strangest landscapes in the known universe. Imagine standing on the surface of a rogue planet. Really try to hold the image. The ground beneath you might be ice nitrogen, ice methane, ice water, ice layered over rock, or it might be bare rock scraped clean by billions of years of micrometeorite impacts in the interstellar medium. The sky above you is black, not the rich star-filled black of a clear night on Earth. Not even the black of Earth orbit where the Milky Way spreads brilliantly from one horizon to the other. Just black, faintly populated with tiny unresolvable points of galaxy light, too dim and too distant to cast shadows, too scattered to read by. No moon, no sun, no sense of east or west or up or down, except the faint pull of the planet's own gravity anchoring your feet to the ground. The silence would not be silence in the way we mean it. Sound requires a medium. The surface of a rogue planet cold enough to have no atmosphere would transmit no sound at all. Nothing to carry vibration. Nothing to carry a voice. Just the direct conduction of vibration through rock, if anything were there to vibrate. And yet deep below you, if the planet is large enough and old enough heat, a slow warmth radiating from the decay of ancient atoms, the same physics that warms Earth's interior and powers its volcanism. A warmth that asks nothing, that needs no star, that simply persists patient and invisible in the dark. Whether anything could live there, whether anything does live there somewhere in the trillion-strong population of rogue worlds now moving through the galaxy, is a question science cannot yet answer, but it cannot rule it out. And in the history of astrobiology, cannot rule it out, has a way of eventually becoming something more interesting. What connects the rogue planets to the wandering stars beyond the surface resemblance of cosmic exile? Is this both tell the same deep story about the impermanence of gravitational arrangements? Stars and planets form together in the same collapsing cloud of gas and dust. They are in a sense born as a family. And then over time, through encounters, through resonances, through the slow grinding of gravitational dynamics across millions and billions of years, some members of that family are separated. Some are cast out to wander alone. Some become suns without worlds. Some become worlds without suns. The galaxy is full of these separations, full of objects that were once bound to something and are now bound to nothing. And yet none of them are truly new stories. Every rogue planet, every hypervelocity star, every wandering world in the dark carries within it the chemical and physical record of its origin. The atoms of which it is made were forged in earlier stars. The architecture of its formation reflects the conditions of a specific time and place in the galaxy's history. It is a message from the past traveling through the present, carrying information that if we could read it fully, would tell us something about where it came from and when and how it came to be alone. The past is never entirely gone. It is just moving sometimes very fast in a direction we are only beginning to learn to follow. Speaking of ancient messages encoded in light, there is another layer to this story that we have not yet touched, the question of what we actually see when we look at these wandering stars in our sky. Because the light reaching our telescopes tonight left some of these stars before the first fish crawled onto land, before the dinosaurs, before the continents were arranged as they are now. We are not seeing where these stars are, we are seeing where they were. And that gap between light's departure and its arrival opens into one of the most quietly astonishing aspects of wandering star science. The light entering your eye right now, from a screen, from a lamp, from the faint glow of a streetlight, through a curtain left, its source a fraction of a second ago. So recent it barely qualifies as the past. But the light from a wandering star, 400 light years away, left that star 400 years ago, before the telescope existed, before Newton was born. What you see in the sky is never now. It is always then. And for some of these wandering stars, then is a very long time ago indeed. There is a concept in astronomy so simple, it sounds almost too obvious to mention, and yet so profound in its implications that astronomers return to it constantly, almost reverently, as a reminder of what it means to study the universe at all. That concept is this all astronomical observation is observation of the past. We do not see the universe as it is. We see it as it was at the moment light left its source and began its journey toward us. The further away a source is, the further back in time we are looking when we observe it. For nearby objects, this delay is negligible. The moon's reflected light is about 1.3 seconds old when it reaches your eye. The sun's light is 8 minutes old. Light from the nearest star, Proxima Centauri, is 4.24 years old when it arrives. For the wandering stars, we have been discussing many of which lie thousands or tens of thousands of light years away. The light reaching modern telescopes may have left those stars when ancient civilizations were still building their first cities, or when the last ice age was retreating from the northern continents, or before the first anatomically modern humans had yet set foot on the soil of what is now Europe. This time delay is not a limitation to be lamented. It is for a certain kind of mind one of the most extraordinary features of the observational universe. Every telescope is a time machine. Every observation is an act of archaeological recovery. When Warren Brown and his team identified that first hypervelocity star in 2005, the light they were analyzing had left the star somewhere between hundreds and thousands of years, before any human had ever considered the possibility that such a thing as a hypervelocity star could exist. The star had already been moving for millions of years before our instruments were capable of detecting it. It did not wait for us to be ready. It simply went. Let's sit with the specific numbers for a moment, because they are the kind of numbers that, if received quietly, can rearrange something inside the way you understand time. HE 0437-5439 is one of the most studied hypervelocity stars in the Milky Way. It was discovered in 2006 using data from the Hamburg/ESO survey, a large-scale survey of stellar spectra conducted using telescopes in Germany and Chile. At the time of its discovery, it was located approximately 200,000 light-years from Earth, well beyond the main disk of the Milky Way, moving at about 723 kilometers per second, fast enough to escape the galaxy entirely. Its trajectory, traced backward through space, appears to originate from the large Magellanic Cloud, a satellite galaxy of the Milky Way, approximately 160,000 light-years away. Think about what that means. The light we use to discover HE 0437-5439 left that star 200,000 years ago. That is before the last common ancestor of modern humans and Neanderthals. That is before Homo sapiens had spread out of Africa. That is before most of the cave art at Lascaux and Altamira was painted. When that light left HE 0437-5439 and began its journey toward what would eventually become a telescope on the surface of Earth, our ancestors were still using stone tools, had no written language, had no concept of stars as other suns, and the star itself was already deep in its intergalactic journey, already far from the large Magellanic Cloud, already committed to a path from which there was no return. We are in that very precise and physical sense 200,000 years behind this story. The ancient Greeks called the planets wandering stars, asteres planeta, and not because they understood them as physical objects moving through space, but because they observed with careful naked eye attention over many generations that a small number of lights in the sky moved against the fixed background of the stars. This observation was enormously important. It set the ancient world on a path of mathematical modeling, of trying to construct geometric systems that could predict where these wandering lights would be on any future night. Hipparchus, working in the 2nd century BCE, produced star catalogs of remarkable accuracy and developed the concept of stellar magnitude, the scale we still use today to describe apparent brightness. Ptolemy, building on earlier work, created a geocentric model of the solar system in the 2nd century CE that was, for all its fundamental wrongness about the Earth's position, mathematically precise enough to predict planetary positions with useful accuracy for over 1,000 years. The reason this history matters here is subtle but important. The ancient astronomers were practicing, without knowing it, a form of the same observational logic that modern astronomers apply to hypervelocity stars. They noticed that some lights moved while others did not. They cataloged the movers. They asked why. They built models to describe and predict the motion. And eventually, through Copernicus, through Tycho Brahe, through Kepler, through Newton, those models converged on an understanding of what the wandering lights actually were. The modern discovery of truly wandering stars is the next iteration of the same ancient observation. Something is moving when it should not be. Something is going somewhere it should not be able to go. The answer in 2005, as in 200 BCE, begins with careful measurement and ends with a physical model that, once understood, makes a kind of inevitable sense. The sky has always held wanderers. We have just needed better tools and more time to find the real ones. Here is a misconception worth addressing carefully, because it affects not just popular understanding, but occasionally appears at the edges of scientific discussion as well. When people first learn that some hypervelocity stars appear to originate from the Large Magellanic Cloud, as HE 0437-5439, seems to the immediate question is, does the LMC have a supermassive black hole capable of producing a Higgs mechanism ejection? The assumption behind the question is that the Higgs mechanism operating at the galactic center is the only route to stellar escape velocity. If the LMC has no such black hole, how did HE 0437-5439 reach its speed? The answer requires a small but important adjustment to the mental model. The Higgs mechanism is not the only pathway. The supernova ejection mechanism can produce high-velocity stars from anywhere in a galaxy where binary systems exist and binary systems exist everywhere. Additionally, the gravitational interaction between the Milky Way and the Large Magellanic Cloud, two galaxies that have been engaged in a complex gravitational dance for billions of years, can itself produce dynamical ejections. Stars in the LMC, perturbed by the tidal forces of the much larger Milky Way, can acquire velocities that, combined with the LMC's own orbital motion relative to our galaxy, are sufficient to produce stars that cross the velocity threshold for escape. This means the population of hypervelocity stars around the Milky Way is not a single homogeneous group with one origin story. It is a mixture, some from the galactic center, some from supernovae and binary systems scattered throughout the disk, some from interactions with satellite galaxies. Each subpopulation carries different information. The galactic center stars tell us about conditions near Sagittarius A star. The supernova ejected stars tell us about binary evolution and white dwarf physics. The LMC origin stars tell us about the dynamical history of the Milky Way's gravitational relationship with its companions. Reading the population of wandering stars is, in a sense, reading multiple chapters of the galaxy's autobiography simultaneously. There is a further dimension of the ancient light story that deserves attention, one that sits at the heart of what makes the study of these stars so philosophically unusual, and that is not often discussed even in careful science communication. When we observe a hypervelocity star and measure its velocity, we are measuring not its current velocity, but its velocity as it was when the light we are observing actually left it. For a star several thousand light years away, that measurement is thousands of years old. The star has continued moving in the intervening time. Its current position is not where we see it. Its current velocity, if it has passed through regions of varying gravitational influence since the light left, may have shifted slightly from what we measure. The star we think we are studying is in the most literal sense a ghost, an image of something that existed in the past moving through a part of space that the star itself has long since passed through. For most astronomical purposes, this discrepancy is manageable through careful modeling. Astronomers account for proper motion, for radial velocity, for light travel time. They project forward using known physics. They say given what we observe here is where this star is now, and here is where it is going. But there is something quietly vertiginous about acknowledging that the observational universe is at every scale beyond the immediate neighborhood, a collection of messages from the past, layered at different distances, representing different moments in cosmic history, all arriving simultaneously at our detectors and requiring careful untangling to reconstruct what was happening when. Have you ever thought about what it would mean to truly see the universe as it is right now all at once? It is in the strictest sense impossible. The universe cannot be observed in the present tense. By the time any light reaches any eye, it is already history. Even the sun you see each morning is 8 minutes old. The nearest star beyond it is more than 4 years old. The Andromeda galaxy visible to the naked eye on a clear autumn night is 537 million years old in the image you are seeing. You are not looking at the universe. You are reading its diary page by page written in light. There is one more connection between ancient light and wandering stars that completes this part of the story, and it involves the way stellar populations age across the history of the galaxy itself. The Milky Way is not a static object. It formed through the gradual merger and accretion of smaller proto-galactic structures over the first several billion years after the Big Bang. Its oldest stars, the metal-poor stars of the galactic halo, orbiting in extended elliptical paths far from the disk, formed when the universe was young and the galaxy was still assembling itself. Some of these ancient stars are more than 13 billion years old, nearly as old as the observable universe. Among the wandering stars we study, some belong to these ancient populations. Their chemical compositions low in the heavy elements that only became abundant after many generations of stellar evolution and supernovae mark them as members of the galaxy's oldest generations. These stars were born in an earlier Milky Way one that looked very different from the elegant barred spiral it has become. They have lived through the galaxy's entire history. They have orbited the galactic center many times over. They have witnessed the formation of every star we can see in the sky tonight. And then, at some point in their enormously long lives, through a gravitational encounter, through a binary interaction, through a close passage near a massive structure, they began moving outward. They became wanderers in their old age after billions of years of belonging. There is something in that which asks to be held gently. A star that belonged for longer than the Earth has existed finally set loose. A star older than our solar system finally free or finally alone, depending on how you choose to read it. The light from these ancient wandering stars carries encoded in the pattern of its spectral lines information that no other source can provide. Each chemical element absorbs and emits light at specific characteristic wavelengths. A fingerprint as unique as a barcode readable with a spectrograph. By analyzing the spectrum of a wandering star, astronomers can determine not just its velocity, but its age, its chemical history, its birth environment. A star born in the metal-poor conditions of the early galaxy has a different spectrum from a star born in the metal-rich conditions of the modern galactic disk. A star that formed near the galactic center, where heavy elements were concentrated by billions of years of stellar evolution, looks different from one that formed in the outer spiral arms. The spectrum is a biography, compressed into light, traveling for thousands or millions of years, arriving at a telescope operated by a species that has been studying the sky seriously for only a few centuries and has only understood what stars actually are for about 100 years. We are young readers of very old messages, and the messages the ancient light of the wandering stars have been traveling toward us for longer than we can truly comprehend. What completes the picture, then, is the question of which specific stars have been identified, confirmed, and individually named in this growing census of the galaxy's exiles. Because astronomy is at its most human, a science of individuals, not just populations and statistics, but specific objects with specific coordinates and specific stories sitting at the intersection of physics and history in ways that reward careful, unhurried attention. In the entire observable universe, roughly 2 trillion galaxies each, containing hundreds of billions of stars, we have positively confirmed by name fewer than 24 hypervelocity stars that are unambiguously escaping the Milky Way. 24, out of what may be hundreds of thousands. We are not short of wandering stars. We are short of the ability to find them. And the ones we have found each carry a story so specific, so individual, that the science of naming them feels less like cataloging and more like meeting someone for the first time. Science is at its deepest level, a science of individuals. Yes, it speaks in populations and statistics and probability distributions. But behind every curve on every graph, there are specific objects, specific stars, specific measurements, specific moments of discovery that give the abstractions their weight and their meaning. And nowhere in the study of wandering stars is this more true than in the small growing catalog of confirmed hypervelocity stars that have been individually characterized, individually named, and individually followed across the sky as the years have passed. Each one is a case study in cosmic violence and cosmic isolation. Each one adds a data point to models that are still being refined. And each one, if you allow it, has something almost like a personality, a combination of speed, chemistry, trajectory, and apparent origin that makes it distinct from all the others. A singular object with a singular history, moving through a universe that has already forgotten the circumstances of its departure. Let's meet some of them. The story of the confirmed hypervelocity stars begins, as we have noted before, in 2005. But the circumstances of that first discovery are worth revisiting in more detail, because they illustrate something important about how science actually works in practice, as opposed to how it is sometimes portrayed. Warren Brown was not in 2005 specifically searching for hypervelocity stars. He was conducting a survey of the stellar halo of the Milky Way, the diffuse, roughly spherical region of old stars and globular clusters that surrounds the galaxy's disk like a faint ancient atmosphere. The survey was designed to study the kinematics of halo stars, how they move, what their velocities tell us about the mass distribution of the galaxy. Brown was taking spectra of blue horizontal branch stars, a class of evolved stars that are relatively easy to identify by their color and spectral characteristics, and measuring their radial velocities, the component of their velocity directly toward or away from Earth detectable as a Doppler shift in their spectral lines. One of those stars had a radial velocity so extreme it appeared to be a measurement error. It wasn't. SDSSJ 0907450 plus 024507. The object in question was moving at a velocity that, when combined with its estimated distance, placed it firmly in the category of unbound, a star moving faster than the Milky Way's escape velocity at its location, headed outward with no intention of returning. Brown published the result. The astronomical community took notice, and almost immediately the search for more began. What is striking about this origin story is the role of serendipity, not randomness, but the kind of prepared mind serendipity that the scientist Louis Pasteur described when he noted that chance favors the prepared mind. Brown was not looking for hypervelocity stars. He was looking at halo kinematics with instruments calibrated to measure velocities, And his methodology was precise enough to catch a signal that would have been easy to dismiss as noise if the measurement had been slightly less clean. The discovery was enabled not by a specific hypothesis about hypervelocity stars, but by a systematic, careful, wide-field survey that happened to include the right star at the right time. Much of science works this way. The discoveries that seem in retrospect to have been inevitable often required a specific combination of instrumentation, methodology, and willingness to take an unexpected result seriously rather than discarding it as an outlier. After SDSSJ0 90745.0 plus 024507, the pace of discovery accelerated. Warren Brown and his collaborators at the Harvard-Smithsonian Center for Astrophysics launched what became known as the MMT Hypervelocity Star Survey, a systematic program using the 6.5-meter MMT telescope in Arizona to search for more stars with extreme velocities in the halo. Over the following decade, the survey identified approximately 24 hypervelocity star candidates, roughly half of which appear genuinely unbound to the Milky Way, based on their measured velocities and estimated distances. Each one added texture to the picture. Some were hot blue massive stars, B-type main sequence stars, or blue horizontal branch stars, the kind of object that lives fast and dies young in stellar terms. Some were in different parts of the halo, at different distances, moving in slightly different directions. Some had trajectories pointing back toward the galactic center. Others did not. The population was even in this small sample heterogeneous, which told researchers early on that hypervelocity stars were not produced by a single mechanism, but by several operating in different parts of the galaxy at different times. One of the most instructive stars in the Brown survey catalog is HVS3, which is also cataloged as HE 0437-5439, the same star we discussed in the context of ancient light. Its position in the survey story is worth lingering on. When its distance was refined using detailed photometric analysis, it became clear that it was located approximately 200,000 light-years from Earth, farther than the Large Magellanic Cloud, farther than any hypervelocity star that could plausibly have originated from the Milky Way's galactic center, and traveled that far in the time allowed by its estimated age and velocity. The galactic center origin was geometrically possible, but the numbers were tight, very tight. This created a scientific puzzle. The star was real, its velocity was real, its distance was real, but its combination of distance, velocity, and estimated age didn't quite fit the galactic center scenario cleanly. The LMC hypothesis that the star originated from a Hills mechanism interaction in the Large Magellanic Cloud, propelled outward by a massive black hole, whose existence at the LMC's center was itself uncertain, at the time, was initially controversial. It required postulating a black hole in the LMC for which direct evidence was limited. Since then, evidence for a massive black hole in the LMC has strengthened, and the LMC origin hypothesis for HE 0437-5439 has gained support, though debate has not entirely closed. What this episode illustrates is how science handles a result that doesn't fit the dominant model cleanly. It doesn't simply accept the anomaly or dismiss it. It examines the assumptions behind every piece of the puzzle, the distance estimate, the velocity measurement, the age determination, the galactic center mass model, and it follows the most parsimonious explanation, while holding open the possibility that the model itself needs revision. In this case, the model needed revision not of the physics, but of the assumption that the Milky Way's galactic center was the only available source of Hills mechanism ejections in the local group. Now, let's turn to a star that offers a completely different kind of story, one whose significance lies not just in its speed, but in what it reveals about the future of the Milky Way itself. Among the hypervelocity candidates identified through the Gaia mission's data, releases a particularly interesting subset, consists of stars whose trajectories, when traced backward, do not originate from the galactic center and do not suggest a supernova ejection history. Instead, their past orbits appear to trace back to the outer disk of the Milky Way, the spiral arm regions far from the center, where conditions are calmer and the stellar density is lower. These stars seem to have been ejected not by a black hole or a supernova, but by the gravitational interaction between the Milky Way and the Large Magellanic Cloud during one of the LMC's recent close passages. The Large Magellanic Cloud is not a passive companion. It is a massive galaxy, roughly 10 billion solar masses in total, with its own dark matter halo, extending far beyond its visible boundaries. And its orbit around the Milky Way brings it close enough to exert significant tidal forces on our galaxy's outer regions. Astronomers studying the Gaia data have found evidence that the LMC's gravity has created a measurable asymmetry in the distribution of stars in the Milky Way's outer halo. A faint but detectable stellar overdensity on one side of the sky caused by stars being pulled toward the LMC's position. And in the most dynamically extreme cases, stars in the outer Milky Way can acquire enough velocity from this interaction to become unbound. This means the LMC is actively ejecting stars from the Milky Way, right now, not from its own center outward, but by gravitationally perturbing our galaxy's outer populations. It is a form of indirect stellar eviction. The LMC does not throw the stars itself, but its gravitational influence weakens the Milky Way's hold on its outermost members just enough for them to slip free. Stars that were Milky Way stars last week in the cosmic sense become intergalactic wanderers simply because a large neighbor passed by. The role of the Gaia satellite in this story deserves particular attention because the transformation it has brought to the science of hypervelocity stars is difficult to overstate. Before Gaia, most hypervelocity star searches were one-dimensional. They measured radial velocity, the component of motion along the line of sight, using spectroscopy. This gave a good estimate of how fast a star was moving toward or away from Earth, but said nothing directly about how fast it was moving across the sky perpendicular to the line of sight. To determine a star's full three-dimensional velocity, you need all three components, the radial velocity from spectroscopy and two components of proper motion, the angular shift in the star's position across the sky over time from astrometry. Proper motion measurements for distant stars are extraordinarily difficult. The angles involved are tiny milliarc seconds per year for nearby stars, microarc seconds per year for distant ones. Before Gaia, only the nearest and brightest stars had proper motions measured with sufficient precision to constrain three-dimensional velocities at the distances typical of hypervelocity stars. The Gaia satellite, with its ability to measure proper motions to microarc second precision for stars across much of the galaxy, changed this entirely. With Gaia data, astronomers can now construct full three-dimensional velocity vectors for stars at distances that were previously inaccessible. This has allowed the identification of hypervelocity candidates that would have been invisible to radial velocity-only surveys, stars whose extreme velocities are mostly in the plane of the sky rather than along the line of sight, and which therefore showed unremarkable Doppler shifts while actually moving at extraordinary speeds in transverse directions. It has also allowed better separation of genuine hypervelocity stars from so-called runaway stars, with high velocities that are still bound to the galaxy moving fast, but not fast enough to escape. The distinction between a runaway star and a hypervelocity star is not merely semantic. A runaway star is unusual, but ultimately gravitationally bound. It will eventually be turned back by the galaxy's pull, its orbit exotic but finite. A hypervelocity star is categorically different. It has exceeded escape velocity and will never return. Gaia has given astronomers the tools to draw that line with unprecedented precision. There is a specific class of object within the hypervelocity star population that has attracted intense scientific interest in recent years, and which deserves its own moment here, the so-called late-type hypervelocity stars, or low-mass hypervelocity stars. The early discoveries, including SDSS J090745.0 plus 024507, and most of the Brown survey candidates were almost exclusively high-mass early-type stars, hot, blue massive objects, several times the mass of the Sun. This was partly a selection effect. High-mass stars are intrinsically brighter, making them detectable at greater distances, which makes it easier to confirm extreme velocities and measure accurate proper motions. But it created a potentially misleading impression that hypervelocity stars were preferentially high-mass objects. The physics of the Hill's mechanism, however, does not strongly prefer high-mass stars. Binary systems across the full range of stellar masses exist near the galactic center, and the slingshot dynamics of the mechanism can, in principle, eject stars of any mass. The prediction was that low-mass hypervelocity stars should exist in large numbers. They would just be harder to find because they are fainter. Gaia has begun to find them. Among the candidates identified in Gaia, data releases several appear to be low-mass cool stars, objects closer in type to our own Sun, with velocities suggesting they are unbound. If confirmed, these low-mass hypervelocity stars would have significantly longer lifetimes than the hot blue stars, meaning they could have been traveling for billions of years rather than merely millions. They would be among the oldest travelers in the galaxy, born perhaps 10 or 12 billion years ago, ejected at some point in the distant past, and still moving, still burning, still carrying their ancient chemistry through whatever void they currently occupy. The thought of a sun-like star, more than 10 billion years old, traveling alone through intergalactic space, burning quietly, maintaining whatever planetary system it might have carried with it, visible only in the infrared and red optical wavelengths of its cool, patient light, is one that rewards sitting with for a moment. Not for analysis, but simply for the scale of it. What does it mean for the science of the Milky Way as a whole, this growing census of its escaped stars? Hypervelocity stars are, among other things, probes of the galaxy's gravitational potential. Their trajectories trace backward through space-encode information about the mass distribution of the Milky Way. How much mass is where, how the dark matter halo is shaped, how the spiral arms and the bar and the bulge together contribute to the overall gravitational architecture. A star that was ejected from the galactic center and has been traveling outward for a known period of time at a measured velocity has taken a path through the gravitational field of the entire galaxy. Every slight deviation from a purely straight-line trajectory reflects the accumulated pull of all the mass it has passed by. This means that the detailed orbits of hypervelocity stars, computed using their measured positions, velocities and distances can be used to constrain models of the galaxy's overall mass distribution in ways that complement other methods. The shape of the dark matter halo, in particular, whether it is spherical or flattened or triaxial, how the density falls off with distance from the center, is something that hypervelocity star trajectories are sensitive to in ways that other kinematic tracers are not. They have traveled farther through more of the halo than almost any other object we can track. They are not just exiles, they are inadvertently cartographers. Their journeys have mapped the invisible structure of the galaxy simply by passing through it. And now with this catalog of individual stars assembled from the serendipitous discovery of SDSSJ 090745.0 plus 024507 in 2005 through the systematic surveys of the Brown team, through the transformative precision of Gaia, we arrive at a question that is perhaps the most intimate and the most unsettling that this entire story has produced. Not a question about the stars themselves, but about the star we know best, the one we live beside, the one that rises every morning and sets every evening and has done so without interruption for 4.6 billion years. What would happen if it were next? What would happen if tomorrow, or 1,000,000 years from now, which is tomorrow on the galaxy's clock? A gravitational event, precise and powerful enough to repeat what was done to SDSSJ 090745. 0 plus 024507, and to US 708 and to HE 04375439 were to find our own sun at the wrong place at the wrong time. That thought experiment has a physics answer, and the physics answer laid out carefully, step by step, is one of the most quietly devastating things that modern astronomy has to say. Imagine waking up one morning and looking out the window and the sun is still there, still rising, still warm, still familiar. But something has changed. Something invisible has happened. Something that, over the next 10,000 years, will unmake everything you know about home. The sun is still burning, but it is no longer where it belongs. It is leaving, and it is taking everything with it, including you. The thought experiment we are about to run is not science fiction. Every piece of physics in it is real. Every timeline is drawn from genuine astrophysical modeling. We are simply applying what we know about escape velocities and gravitational dynamics and the structure of the solar system and the requirements for planetary habitability to a scenario that, while extraordinarily unlikely for us specifically, has already happened to at least a dozen confirmed stars and almost certainly to hundreds of thousands we have not yet found. What if the sun were ejected from the Milky Way, not as a metaphor, not as a narrative device, but as a physical event governed by the same equations that govern HE 0437-5439 and US 708 and SDSSJ 090745.0 plus 024507? What would actually happen? When, in what order, and what at the end of it all would remain? Let's follow it carefully from the first moment to the last. The event itself would be instantaneous in cosmic terms. If triggered by the Hills mechanism, the disruption would be sudden and gravitationally decisive. A binary companion, if the sun had one, would be captured. The sun would be flung outward. If triggered by a supernova in a hypothetical binary partner, the explosion would last seconds and the sun would be released from its orbital bond, almost before any signal of it could travel to Earth. For the purposes of this thought experiment, let us say that the sun has been set on a trajectory that will, over the course of several million years, carry it out of the Milky Way entirely. It is moving fast somewhere between 500 and 700 kilometers per second, fast enough to eventually exceed the galaxy's escape velocity from our current position. The planets held in their orbits by the sun's own gravity rather than the galaxies come along. The solar system as a gravitationally self-contained unit departs intact. So in the first moments, in the first years, the first centuries, nothing visible changes. The sun still rises. The seasons still cycle. Earth still orbits in its comfortable habitable zone, roughly 150 million kilometers from the solar surface, receiving the same 1,361 watts per square meter of solar energy that it receives today. The moon still circles overhead. The night sky looks identical to the sky you know. The only thing that has changed is a number in a physicist's notebook, the velocity of the sun relative to the galactic center. A number that means nothing for a human lifetime or 10 or 100. But numbers in physics are patient. Let us move the clock forward 1 million years. At a velocity of roughly 600 kilometers per second, the sun has now traveled approximately 600 parsecs, about 1,950 light years, from its former position in the Milky Way's Orion arm. It is still technically within the disk of the galaxy, but it is moving through a less densely populated region, and its trajectory is already taking it above the galactic plane into the lower density halo. The night sky from Earth has begun to change. Not dramatically, not in a way noticeable from one generation to the next, but over 1 million years, proper motions accumulate. The stars we know, Sirius, Vega, Betelgeuse, the familiar constellations have shifted from their positions. New bright stars occupy new positions. The Milky Way still stretches across the sky, but its orientation has changed. We are no longer in the same arm. We are no longer surrounded by the same stellar neighborhood. For life on Earth, nothing has changed materially. The sun's energy output is essentially unchanged. Earth's orbit is essentially unchanged. The temperature of the planet is governed by the sun, not by the galaxy, and the sun has not changed. The biosphere is intact. Humans, or whatever their descendants might be, are entirely unaware that anything has happened on any scale larger than their daily lives. But the address has changed. Quietly, invisibly, permanently. 10 million years. Let the clock move again. The sun is now well outside the Milky Way's disk. It has left the spiral arm structure entirely and is moving through the diffuse stellar halo, the sparsely populated outer region, where old metal-poor stars orbit in extended eccentric paths. The density of stars around the solar system has dropped dramatically. Where once the nearest stellar neighbor was about 4.24 light-years away, the nearest star is now likely many tens of light-years distant. Stellar encounters already rare have become vanishingly infrequent. The night sky from Earth has transformed significantly now. The Milky Way, the band of light that meant the galaxy was all around us, has shrunk and shifted. It has become something more like a bright extended object in a specific direction, rather than an encompassing arch across the full sky. It is visibly receding. Where once the galaxy was our context, our neighborhood, the structure within which our star was embedded, it is becoming something we observe from the outside, an object rather than a home. Our descendants would be looking back at the galaxy rather than from within it. For life on Earth, still nothing has changed materially. The sun still burns. The planet still orbits. The seasons still turn. The danger is not in these first tens of millions of years. Here is a question worth pausing on, because it reveals something important about where the real risk in this scenario actually lies. And it is not where most people would instinctively guess. When people are asked, what would happen to Earth if the sun left the Milky Way, the most common answer involves the cold. The idea that without the galaxy, without neighboring stars, without something to provide additional warmth, Earth would freeze. This intuition misidentifies the sun's galactic context as a source of heat for Earth. It is not. The energy reaching Earth's surface comes from the sun alone. Other stars are too far away to contribute measurable heat. The galaxy's radiation environment contributes a small, diffuse background, but its removal would change Earth's energy budget by an amount so tiny no instrument we possess could detect it. The real risks in a wandering solar system are subtler, and they operate on much longer timescales. The first involves the Oort cloud, the vast, roughly spherical shell of icy bodies orbiting the sun, at distances between roughly 2,000 and 100,000 astronomical units thought to be the source of long-period comets. The Oort cloud's outer regions are weakly bound and sensitive to perturbations from passing stars and the galactic tidal field. In a normal galactic environment, these perturbations occasionally dislodge Oort cloud objects and send them inward as comets. As the sun transitions through different galactic environments and eventually into the intergalactic medium, the perturbation pattern changes. During transitions through denser regions, comet showers could temporarily increase, raising the probability of large body impacts with the inner solar system. In deep intergalactic space, by contrast, the Oort cloud would experience almost no external perturbations. At all, long-period comets would become extraordinarily rare, the inner solar system growing quieter than it has been at any point in its history. The second risk involves planetary stability over timescales of billions of years. The solar system's long-term orbital dynamics are governed primarily by the sun's gravity and mutual planetary interactions with galactic tidal forces, playing a very minor but non-zero role over geological and astronomical timescales. Removing that galactic tidal field changes the long-term evolution of the outer solar system in ways that planetary dynamicists are still working to fully characterize. The effects are small, but small effects integrated over billions of years can produce detectable consequences. 100 million years. By this point, the Sun is likely in the outermost, most diffuse regions of the Milky Way's dark matter halo, or just beyond it. The galaxy, all 400 billion stars of it, is now a distant, beautiful object in the sky. From Earth, it would appear roughly as Andromeda appears to us tonight, an elongated smear of light, visible to the naked eye, if the sky is truly dark, spanning several degrees of arc. Our home galaxy. No longer our home. Here is where something begins to change for the long-term habitability of Earth, not catastrophically, and not because of the galaxy's absence. The Sun, like all main sequence stars, is slowly brightening over its lifetime. Stellar evolution involves a gradual increase in luminosity as the helium ash in the core builds and the hydrogen-burning shell adjusts. Over its full lifespan, the Sun will become significantly brighter. This brightening is already happening and is entirely independent of the Sun's position in or out of the galaxy. In approximately 500 to 800 million years from the present, the increasing solar luminosity is expected to push Earth's surface temperature past the threshold for a runaway greenhouse effect, the loss of surface liquid water, driven not by human activity, but by stellar physics. This timeline is unchanged by whether the Sun wanders or stays. The galaxy has nothing to do with it. The star does not know it has left. 1 billion years into the journey, the solar system is now in intergalactic space. The Milky Way is a distant galaxy, perhaps third or fourth apparent magnitude, to any eye that might still be looking at the sky from Earth's surface, distinguishable from other distant galaxies only to a careful observer who knew what to look for. The cosmic web is unchanged. The void has deepened to its full depth. Earth in its natural state has long since passed the threshold for surface habitability. The Sun has brightened noticeably over its 5.6 billion years of existence. Whatever life existed on Earth's surface in the geological present has either adapted in ways beyond our ability to predict, migrated to subsurface environments sustained by geothermal heat, found refuge in ocean depths, or ceased. This is not a consequence of the Sun's wandering. It is a consequence of the Sun's aging, a process entirely internal to the star, proceeding on a schedule set at the moment of the Sun's formation, modifiable by nothing in the galaxy. The Sun, though, is still burning. It will continue to fuse hydrogen in its core for another approximately 5 billion years. Then it will expand into a red giant, likely engulfing Mercury and Venus, and possibly Earth, depending on the precise dynamics of its mass loss and expansion. It will shed its outer layers into a planetary nebula, a beautiful ephemeral cloud of ionized gas expanding outward at tens of kilometers per second, glowing in reds and blues and greens from the emission of excited atoms illuminated by the hot white dwarf remnant at its center. That white dwarf will cool for the next trillion years, slowly fading from white to yellow, to orange, to red, to black. A dead star in intergalactic space surrounded by the cold remnants of its planetary family, in darkness so complete that the nearest galaxy is many millions of light years away. A quiet end. In the most complete isolation the universe can offer. What does this thought experiment teach us when it is laid out fully? The first lesson is one of perspective. The fate of Earth, of life, of everything we have ever known or built or loved, is not threatened by the galaxy. It is not the galaxy that gives us warmth or seasons or the conditions for life. It is the Sun. The galaxy is our address, not our home. Our home is the solar system. And the solar system is in all the ways that matter for life self-contained. Remove the galaxy and almost nothing changes for the next 100 million years. What threatens the long-term future of life on Earth is the star itself, brightening, aging, evolving, not the community of other stars it currently moves among. The second lesson is one of deep gratitude for time scale. The Sun is 4.6 billion years old. It has another approximately 5 billion years of main sequence burning remaining. The window of time during which Earth's surface is habitable, roughly between the formation of the oceans and the onset of the runaway greenhouse effect, spans perhaps 1 billion years from the present, a number that is almost impossible to fully hold. But that represents something like 200 million human generations of future time. Whether the sun stays in the Milky Way or wanders into the intergalactic void does not significantly compress that window. What we have been given by the accident of stellar physics and planetary formation and galactic positioning is a span of time so vast that human civilization, even at its oldest reckoning of 10,000 years, represents less than 100,000th of the remaining habitable period. The third lesson is perhaps the most quietly startling. The stability we experience, the sun in its orbit, the planets in their places, the galaxy around us is real. But it is not guaranteed. It is the product of a specific gravitational configuration that has persisted for 4.6 billion years, and that the laws of physics do not promise to maintain forever. We are not immune to the forces that have exiled other stars. We are simply lucky in the most measurable, most physical, most non-metaphorical sense of that word, that those forces have not yet found us. Tonight, the galaxy is still all around us. The stars we see are neighbors moving in the same gravitational structure, belonging to the same turning wheel of matter that includes our own sun. The Milky Way stretches overhead, not as a backdrop, but as a community. And the wandering stars, the ones that have left the ones that are leaving the ones that will never find their way back, are out there in the dark, burning alone, carrying in their light the record of a belonging that ended in an instant of gravitational chance. Which brings us finally to the question. This entire journey has been circling, without quite naming, what does it mean in the deepest, most honest sense that physics will allow for anything to be home? What is the difference between a star that belongs to a galaxy and a star that has been cast out? The math is clear, the physics is clear, but beneath the math, beneath the physics, there is a question that belongs to something older than either something that has been asking itself in one form or another for as long as there have been minds capable of looking up at the sky and wondering why some lights move while others hold still. That is the question the final part of this story will try to answer, not with equations, with something quieter. Here is something the universe has never told you directly, but has been showing you every clear night of your life. You are already moving, right now, this moment. While you lie still, while you breathe slowly, while the room around you holds its quiet, you are aboard a planet orbiting a star at 67,000 miles per hour. That star is orbiting the center of a galaxy at 514,000 miles per hour. That galaxy is falling toward a supercluster at roughly 1.4 million miles per hour. You have never, not once in your entire life, been still. You just couldn't feel it. We have traveled a long way tonight, from the first hypervelocity star discovered in 2005 to the ancient light of HE 0437-5439, 200,000 years old before it reached a telescope, from the Hills mechanism near Sagittarius, a star to the billion-year thought experiment of a wandering sun carrying Earth through intergalactic darkness, from rogue planets with no stars at all to the strange hot emptiness of the intergalactic medium, from the ancient Greeks looking up at their asteres planetae to the Gaia satellite mapping the three-dimensional velocities of 1 billion stars with microarc-second precision. It has been a long journey, and before it ends, it deserves a question worth sitting with, honestly. What is the line, the actual physical line, between a wandering star and a star that belongs? You might think the answer is simple: escape velocity. A star moving faster than the Milky Way's gravitational escape velocity at its location is unbound. A star moving slower is bound. Clean binary mathematical. And yes, that is the formal definition. But here is what makes it strange when you look at it closely. Our sun right now is moving at about 514,000 miles per hour around the galactic center. The Milky Way's escape velocity from our position is roughly 1.2 million miles per hour. We are moving at about 43% of escape velocity. We belong, we are bound. The galaxy holds us. But that number, 43%, is not a law of nature. It is a current condition. It is the result of 4.6 billion years of a particular history in a particular region of a particular galaxy under a particular set of gravitational influences. The sun has that velocity because of how it formed, where it formed, and what it has and has not encountered in the years since. A slightly different molecular cloud, a slightly different galactic neighborhood, a slightly different timing of a gravitational encounter that never happened. Any of these could have produced a sun moving at a different speed in a different direction, and the line between belonging and wandering would have been drawn in a different place. The wandering stars are not different in kind from the stars that stay. They are different in circumstance. The same physics applied with slightly different initial conditions, or slightly different gravitational histories, produces exile instead of community. The universe does not distinguish between them. Gravity does not judge. It simply pulls or fails to pull based on the numbers. Carl Sagan once wrote in that calm, precise, slightly heartbreaking way he had that we are a way for the cosmos to know itself. The atoms in your body were forged in stars. The calcium in your bones came from supernovae. The iron in your blood was synthesized in the cores of stars that exploded before the sun existed. You are in the most literal chemical sense made of star stuff. This is not a metaphor. It is nuclear physics. But here is the extension of that thought that rarely gets made explicit. Some of those stars, the ones whose atoms you carry, may have been wandering stars, may have formed in a different part of the galaxy, or even in a satellite galaxy, been ejected and spent millions of years crossing intergalactic space, before their material was recycled into the interstellar medium, mixed into a molecular cloud, and eventually incorporated into the solar nebula that formed the sun and everything orbiting it, including Earth, including you. You cannot know this for certain. The atoms do not carry records of their stellar origins in forms we can currently read. But the probability is not negligible. The galaxy has been processing stellar material for 13 billion years. Wandering stars have been returning their mass to the interstellar medium through stellar winds, through planetary nebulae, through supernovae for that entire time. Some fraction of every star, every planet, every living thing in the Milky Way contains material that has passed through the interior of a star that no longer belongs to any galaxy. You may be in part made of exile, and if that is true, if the wandering is in you at the atomic level, then looking up at the sky and wondering about hypervelocity, stars and rogue planets and intergalactic darkness is not just curiosity. It is in some small and genuine sense recognition. Now here is a question that came up during the research for this story, one that I genuinely find myself returning to, because the answer is both obvious and somehow still surprising every time. If a wandering star has been traveling through intergalactic space for, say, 5 billion years, if it left the Milky Way or its satellite galaxies around the time our solar system was forming, where is it now? At 800 kilometers per second traveling for 5 billion years, it has covered approximately 4.2 million light years. That is roughly the distance to the Andromeda Galaxy from our position. A star ejected 5 billion years ago at reasonable hypervelocity, speeds could right now be entering the vicinity of another major galaxy drifting toward the gravitational embrace of a new galactic system after 5 billion years of solitary travel. It would not be captured easily. Gravitational capture requires losing energy, which requires interaction, which requires time and proximity. But it could, over further billions of years, find itself influenced by a new galactic gravitational field, becoming eventually a halo star of a galaxy it did not form in, a traveler that arrived after unimaginable patience somewhere new. Is that arrival after 5 billion years of empty space a kind of homecoming? Or is it just the next chapter of the wandering physics does not answer that question? But the fact that the question can be asked, that the time scales and distances involved, allow for the possibility of a star being born in one galaxy, ejected crossing intergalactic space, and arriving in the gravitational vicinity of another galaxy over cosmic time, is one of the things that makes astrophysics at its best feel less like a technical discipline and more like a particularly well-sourced form of wonder. Let's return for a moment to the stars themselves, not as data points, not as catalog entries, but as objects. A hypervelocity star moving through intergalactic space is from a purely physical standpoint perfectly ordinary. It is fusing hydrogen in its core, or helium, or in its later life, some sequence of heavier elements. It is generating light. It is maintaining a surface temperature and a luminosity appropriate to its mass and age. It is by every intrinsic measure indistinguishable from a star sitting quietly inside a galaxy. The astrophysics of stellar interiors is determined by local conditions, pressure-temperature composition, not by galactic location. A star is a star, whether it has a galaxy or not. And yet, there is something in the concept of a star with no galaxy, no gravitational community, no neighboring stellar systems, no molecular clouds nearby to form new stars, no possibility of ever being part of a system with planets and chemistry and the long, slow work of a biogenesis that resists being reduced entirely to neutral physics. Not because physics is insufficient, but because we are the ones doing the physics and we carry within us an awareness of what it means to be alone that no instrument can fully neutralize. The wandering star does not know it is alone. It has no interiority, no awareness, no longing. It burns because nuclear physics requires it to burn. It moves because gravity arranged it to move. It does not grieve its origin or anticipate its destination. It simply is, in the clearest, most unambiguous sense of the word, doing what it does, in the place it finds itself with no commentary and no complaint. And there is something in that, in the star's absolute and unconcerned existence in the face of the most extreme isolation the universe can arrange that is quietly, unexpectedly steadying. The universe does not require its wanderers to be troubled by their wandering. It only requires them to burn. Here is the data that closes the circle of this entire story, the number that ties together everything from the ancient Greeks to the Gaia satellite to the thought experiment of a wandering sun. The Milky Way is estimated to contain somewhere between 100 and 400 billion stars. Current models of the Higgs mechanism operating near Sagittarius. A star suggests a rate of hypervelocity star production of roughly one star every 100,000 years. Over the 13 billion year history of the galaxy, that rate, if roughly constant, which it has not been but as an order of magnitude estimate, implies somewhere in the range of 100,000 to a few 100,000 hypervelocity stars ejected from the Milky Way over its lifetime. Additional ejections from supernovae, from galactic interactions with the LMC, and other satellites from cluster dynamical ejections, these add to the total. The true number of stellar exiles produced by the Milky Way across its history likely runs into the hundreds of thousands, possibly more. We have confirmed fewer than 24. The rest are out there beyond the galaxy, or crossing it, or deep in the halo, moving in directions and at speeds. We have not yet measured carrying chemical compositions. We have not yet read tracing trajectories we have not yet reconstructed. The sky is full of wanderers we have not yet met. The universe has been ejecting stars for longer than the Earth has existed, and the census has barely begun. The Gaia mission continues. Its fourth data release, anticipated in coming years, will add hundreds of millions of new stellar measurements to the catalog. Future missions, including proposed successors to Gaia with even greater precision and fainter limiting magnitudes, will push the survey deeper into the halo and farther beyond the disk. The James Webb Space Telescope, with its extraordinary infrared sensitivity, is already detecting free-floating planetary mass objects in star-forming regions that would have been invisible to any previous instrument. The catalog of wanderers is going to grow. The stories are going to multiply. And every new wandering star confirmed is another data point in what may be the longest longitudinal study in the history of science, the story of how a galaxy makes and unmakes its own community of stars over 13 billion years of gravitational evolution. The night sky. You see when you step outside, if you are in a place dark enough to see it properly, which increasingly requires effort and intention, is an archive. Not a static image, but a dynamic, evolving record of billions of years of stellar birth, death, movement, and loss. The stars you see are not where they are. They are where they were when their light left them. Some of them are no longer there at all, already evolved into white dwarfs or neutron stars or black holes, their visible light replaced by radiations our eyes cannot detect. Some of them are moving right now, at speeds that by the time their light reaches a future telescope will have carried them measurably from where they appear tonight. And somewhere in that sky, invisible without instruments too faint and too far for naked eye observation, there are the wanderers, the exiles, the stars that used to have a galaxy and now have only speed and darkness and the long, patient burning of nuclear physics in the void. They are out there. They have always been out there, ever since the first one was thrown free of the first galaxy to be disrupted by the first supermassive black hole to form in the young universe. They were out there when the Greeks were watching their Asteras Planetae. They were out there when Newton was inventing the mathematics to describe gravity. They were out there when Hubble was discovering that the nebulae were galaxies, when Einstein was writing the field equations, when the first radio telescopes opened new eyes to the sky. We simply didn't know to look. And then, in 2005, Warren Brown looked not for them exactly, but with instruments careful enough to catch them, and the catalog began. What I find myself thinking about at the end of all of this is not the most dramatic numbers, not the 3 million miles per hour speeds, not the 200,000-year-old light of HE 0437-5439, not even the trillion rogue planets drifting through the galaxy in permanent darkness. What I find myself thinking about is the ordinary, uncelebrated stability of what we have. The Sun is 4.6 billion years old. It has completed roughly 20 orbits of the Milky Way in that time. In all of those orbits through the gravitational fields of spiral arms, and the galactic bar, and molecular cloud complexes and occasional near misses with other stars, it has remained bound. The galaxy has held it. The solar system's architecture has remained intact. The Earth has remained in its habitable orbit. And on this small, warm, stable world, something arose that could look up at the sky and wonder about the stars that didn't stay. That is not a trivial piece of luck. It is an enormously improbable, astronomically specific, gravitationally maintained piece of circumstance that has continued without interruption for long enough to produce everything you have ever known or felt or thought. The wandering stars remind us of this, not by threatening it. They are far away. They are few in number relative to the total stellar population. They pose no danger to us, but by illustrating the alternative, by showing us what a star looks like when the circumstances that hold it in place are removed, by being in their unending solitary travel, the counterfactual that makes the ordinary extraordinary. You are not on a wandering star. You are on a planet orbiting a star that has for 4.6 billion years remained within the gravitational community of a galaxy. The galaxy has been your address, and the sun has been your anchor. And the ordinary blue sky above you, which you can only see because the sun is close enough and stable enough to illuminate it, is the evidence of that stability renewed every morning. The wandering stars will never see a blue sky. They will never have a morning. They will burn, and they will drift, and they will carry their light outward through a darkness that grows only deeper as the universe expands, and eventually, in billions of years, they will go cold, and the darkness will be complete. We are not them. We are the ones who stayed. The ones the universe arranged just this once, just this carefully, to remain long enough to look up and notice that some stars are missing. Sleep well tonight, knowing that the sun will rise again right on schedule exactly as it has for 4.6 billion years, exactly as it will for billions more. Not because the universe owes it to you, but because the numbers this time happen to work out in your favor. And if you found something in tonight's journey, something that settled in you, or opened something up, or made the darkness outside your window feel a little less like nothing and a little more like a story still being written, then you already know what to do. Like this video if it gave you something to carry into sleep. Subscribe if you want to keep drifting like this into the quiet corners of science that most people never stop long enough to reach. Ring the bell not for urgency, but so the next quiet night finds you when it's ready. The universe has more stories than any one night can hold. There are black holes that sing in gravitational waves. There are neutron stars spinning 716 times per second, so dense that a teaspoon of their material would weigh 1 billion tons. There are galaxies so old, their light has been traveling since before the Milky Way existed. There are questions so deep that answering one reveals 3 more waiting just beneath. We'll get to them, one quiet night at a time. For now, let the wandering stars go where they are going. Let them burn in their darkness, patient and indifferent and magnificent. And let yourself rest in the warmth of a sun that stayed. Sleep well, drift gently. Good night.